So thank you for the introduction. I want to say two things before I start the talk. So if you're interested in this topic, a lot of the work I'm going to be discussing today can be found in this work from this 2016 paper or our more recent work from this paper in 2022. So I've linked these archive IDs so you can check them out afterwards. The second thing I want to say is that it's a really an absolute pleasure to be here speaking on behalf of Google's Quantum AI team at this Moonshot Goal 6 International Symposium on behalf of the whole team, but really the co-authors that I've listed here. So let's get started. So the outline of today's talk is as follows. In the first section, I want to cover the basic physics of dispersive measurement systems so that we have an understanding of the physical systems in which these measurement-induced state transitions are occurring. Then I want to cover the history of measurement-induced state transitions, and really what I want to do there is recap all of the physics that was understood about measurement-induced state transitions to about the 2016 mark when this first paper came out. Once we understand the history, I want to go into the motivation behind why we're working on what is now nearly a decade-old problem. Once we understand that motivation, I want to go into how we characterize measurement-induced state transitions in an experiment so that you can take these techniques home with you and start studying MIST with us. Rather than just checking out these papers and looking at how awful it kind of appears at a glance. Then I want to cover some of the observations that we've made while studying measurement-induced state transitions in the regime where our resonator is operating below our qubit in frequency. And I know that this sounds kind of random, but this turns out to be a really relevant limit to be working in to achieve a ultra-fast qubit reset gate. So it turns out that there's some really significant both qualitative and quantitative differences that emerge whether or not your resonator is operating at frequencies above or below your qubit from the point of view of measurement-induced state transitions. If time permits, I want to go into some potential future directions for how we might be able to mitigate these in the future. Okay, so dispersive measurement systems, how do they work? So a typical dispersive measurement system consists of the following two circuit elements, at least in terms of a circuit QED system. So on the left-hand side, you have an LC oscillator, and on the right-hand side, I've drawn a fixed frequency transmon qubit. These two oscillators are capacitively coupled, and so they have some type of charge-charge interaction. What I've drawn below them are the potential energy landscapes for these two circuits, and then the wave functions represented in either the flux or phase basis. Now, the details and annotations on this figure are not so important, but what I'm trying to do is remind the audience that we're really looking at multi-level systems. In the case of the harmonic oscillator, this is a multi-level linear system. In the case of the superconducting transmon qubit, this is a multi-level nonlinear system. And the multi-level nature of these two circuits is really important for determining when state transitions happen and why. So keep this in mind. And I mean that not only in the trivial sense, because a state transition is kind of defined as measurement-inducing leakage out of the computational subspace. So of course you need multiple levels for that to occur. But really, it actually turns out that depending on whether your resonator is above or below your qubit, these transitions happen for different reasons. And this comes back to this multi-level energy structure of these two systems. Okay, so enough words on that. The Hamiltonian for this system is given by this equation on the top right. So we have our harmonic oscillator's energy term, we have the qubit's energy levels, and then we have this charge-charge interaction terms between these two systems. As an experimental physicist, or really just as a physicist in general, when I look at a Hamiltonian like this, I ask the question, how can I simplify this Hamiltonian? So the first thing that you might be tempted in doing is making the so-called rotating wave approximation. What that boils down to is you go into the interaction picture of these two bare Hamiltonians. You see all of the terms that oscillate fast, and you can neglect the fast oscillating terms in favor of the terms that either don't oscillate at all or oscillate at the difference frequency between these two systems. When you move back into the lab frame, what you end up with is this Hamiltonian, which is slightly simpler. It's collapsed this double summation into a single summation, which connects transmon states that differ by one excitation, and it's coupled to the creation and annihilation operators of the harmonic oscillator. So this is the typical transverse interaction between a harmonic oscillator and a multi-level nonlinear system. And all this work was pioneered back in the 1960s, and I find it kind of astonishing that we're still learning about this system today. So these are the kind of landmark papers on this topic. Now, the next thing that you might be tempted to do is make the two-level system approximation. So you pretend for a second that this transmon is really a two-level system described by the Pauli matrices, and what do you know, out pops this celebrated Jaynes-Cummings Hamiltonian. So we're making some progress here. I'm sorry, I'm an experimentalist and I'm explaining a bunch of math in the morning, but I promise we'll get to the point here pretty soon. So the next thing that we want to do is we want to make the so-called dispersive limit. What this boils down to is you say that the coupling strength between this qubit and resonator is significantly smaller than the detuning or the frequency difference between this qubit and resonator. And in that limit, you can show that this effective Hamiltonian emerges, which says that if the qubit has one state, the harmonic oscillator will have one frequency, and if the qubit's in the excited state, it will oscillate at a different frequency. And this is the basic idea behind dispersive measurement. So you have two frequencies on this resonator, depending on what state the qubit is in, and then you typically operate this system by either coupling in a reflection circuit or a transmission circuit, and then the amplitude and phase of the signal that scatters off of this resonator gives you information about the state of the qubit. Now, out of this analysis pops a couple of additional interesting parameters. So this is dispersive shift chi, which is half the difference between these two dressed resonator states corresponding to the qubit ground and excited state. There's obviously this detuning parameter here, and then there's this qubit resonator coupling efficiency, which goes as the geometric mean of the frequencies divided by 2, multiplied by some measure of the capacitive coupling efficiency between these two modes. Now, another parameter that comes out of this analysis is this critical photon number. And this critical photon number is in some ways a measure of how strongly mixed these two systems are. What I mean by that is that if you're operating with a number of photons that is significantly less than n crit, then you can kind of pretend that these two systems are really weakly hybridized. However, if you're operating with a number of photons comparable to or larger than the critical photon number, then you really need to take into account that these two systems are really strongly mixing. Okay. So just to give you kind of an example of how this multi-level nature of the transmon is really important, if we perform all of these approximations, but instead of truncating to the lowest two energy levels of the transmon, we include the fact that the transmon has a second excited state, then we'll realize that this dispersive shift, g squared over delta, which I was mentioning before, undergoes a very significant renormalization. And in practical situations, this renormalization chi, which I guess is showing up here as a box, is reduced by a factor of the qubits and harmonicity divided by the detuning, which in practical situations is on the order of maybe a fifth to a tenth. So this is telling you that these higher level transmon states are playing a very important role in dispersive measurement systems, and if you want to understand dispersive measurement, you really shouldn't be neglecting them. Okay, so enough recap. Now let's talk about what was understood about measurement-induced state transitions in our first work on this topic. So back in 2016, Daniel Senk, Mustafa Kezri, and Jimmy Chen devised an interesting experiment to study these systems. Just to maybe unpack things a little bit here, for those of you that aren't used to thinking about IQ clouds and things like that, this is the response of the resonator after some integration. These circles represent basically the Gaussian centers corresponding to each of these qubit states that's indicated in the legend. So if you see a ton of density here, that means that the qubit is in the ground state. And if you see a ton of density in this cloud, it means it's in the excited state and so on. So in these experiments, what they did was as follows. They prepared the qubit in its ground state. They then drove the resonator using a 2 microsecond long variable strength stimulation pulse. They allowed 500 nanoseconds for the resonator to ring down, which was suitable for their system. And then they measured the state of the qubit after the resonator had returned to vacuum, asking the question, where did the qubit population end up as a result of this stimulation pulse? What they found was that at low dry power, the qubit behaved roughly as expected. You see a high density in the ground state, and then a little bit of ground state preparation error. This is kind of normal for our weakly nonlinear systems because they undergo things like heating. But as they cranked up the resonator dry power, they saw that they were losing population to states significantly beyond even the state 3. So you might be tempted to assign this position here to maybe state 4, but out here is kind of anyone's guess. And as they increased the power even further, they lost more and more population of the ground state to these higher excited states. Interestingly, after talking with Daniel a little bit about this experiment, what he mentioned was that as they increased the power even further, they saw that the system started to kind of come back to almost behaving like it was in a ground state. And this was the first indication that you were dealing with some type of energy resonance in the system. So the question was, why is this happening? Is it related to the critical photon number, or is it something else? So fortunately for us, we worked with some really good theorists, and Mustafa Kezri and Alexander Korokov went and crunched the numbers on this system, and they came back and they said that for the Hamiltonian that we've been considering, it's not possible that this is occurring. But they did notice that the Hamiltonian that they were analyzing was, they had made an approximation, namely the rotating wave approximation. Why this is interesting is that if you inspect the energy level structure of this system and you don't make the rotating wave approximation, then you see that interesting resonances start to emerge between different RWA strips. Now that begs the question, what the hell is an RWA strip? So let me explain. The way these kets are labeled is the qubit state is the first position, the resonator state is the second position, and an RWA strip is given by one of these strips here. What this is a strip which conserves the total number of excitations in these two systems, and this is equivalent to making the rotating wave approximation. Maybe a little bit more to unpack here is if you focus on a fixed column and you go up in state, you're increasing the total number of excitations in the system by 1 unit. And what they noticed was that these resonances were emerging between RWA strips that differed by maybe 1 or 2 total excitations. So the individual processes that they suspected were occurring weren't conserving energy, but the overall process that was taking you to this final state was conserving energy. So this was kind of an interesting discovery, and they began to kind of crunch the numbers. This is, instead of looking at the bare eigenenergies, looking at the dressed eigenenergies of this system as a function of the photon number in the resonator, and indeed what they saw was that the qubit ground state was beginning to collide with the 6-qubit excited state at some particular photon occupancy, and similar things were happening for the qubit 1 state. So this was kind of a smoking gun that indeed making the rotating wave approximation in this system is a very bad one. Just to show you how well this theory works, this is a plot of the expected photon number and qubit frequency at which a state transition should occur in this system for 2 of the most problematic transitions, and then the circles and squares indicate the experimentally extracted positions. And this was done with no free parameters, and this was really a slam dunk telling us why this is happening. Okay. So now the question comes down to, if you have this really satisfactory model of these measurement-induced state transitions, why are you still working on the problem, right? It's solved physics. So it turns out the answer to that question is kind of twofold. Number one, dispersive measurement is actually quite slow in superconducting qubits. So if you look at a typical surface code timing cycle, you have some single qubit gates, you have 4 layers of CZs, maybe another single qubit gate, and then the readout starts. And this timing diagram is not to scale, as I'm going to explain. If we assume something like 25 nanoseconds for single qubit gates and 2 qubit gates, and then we have 4 layers of 2 qubit gates, then this boils down to about 150 nanoseconds for the unitary operations. Then if we go to the measurement, we're looking at something on the order of maybe 250 to 500 nanoseconds in duration for a typical multiplex measurement. So this is telling you that this readout process is consuming something like 60 to 80% of a surface code cycle. And while that's happening, your data qubits are idling, they're decohering, and this is bad news. So we'd really like to shrink this down. Now, one obvious way to shrink this timescale down is to simply drive this resonator harder, but as I've just said, as you increase the photon number, the likelihood that one of these state transitions occurs increases. So this is kind of a problem. The other interesting thing to note is that error correction in these superconducting circuits really seems like it's going to require some type of fast qubit reset. And the reason for that is that these weakly nonlinear systems build up a lot of leakage as you operate them. What I mean by this is that during gates, both single and 2 qubit, and then also during readout, you put leakage into these measure qubits, also into data qubits, it turns out. And so you need some way of removing entropy from this system periodically in order to return your measure qubits and data qubits into the computational subspace. Now, one way that we've found that works quite well is that you can leverage this ultra-strong coupling between your qubit and resonator to basically perform an adiabatic swap. So if the qubit is occupying states, let's say 1, 2, or 3, you can do a nice, really fast adiabatic swap gate between your qubit and resonator. But unfortunately, this requires you to put your resonator below your qubit rather than above like we conventionally operate. This is just to show you the type of reset error that we can achieve with this protocol. So in something like 250 nanoseconds, we can reset states 3, 2, 1, which is pretty good. And you'll notice that the dominant cycle time here is limited by how fast our resonator decays, and we were using kind of modest parameters in this setup. It turns out that increasing the resonator decay rate is not only favorable for fast reset, but also for fast readout. So, okay. This is worth noting, but again, remember that the resonator needs to be below our qubit. Now, why do I keep saying that? Well, if we look at our energy level structure from before where these non-RWA transitions were occurring, and we compare it to this new configuration when our resonator is below our qubit, we notice that the energy level structure is drastically altered. In particular, the interesting resonances that begin to emerge between the transmon and higher excited states are not across RWA strips, but actually within an RWA strip. In other words, these are the problematic resonances that occur here, and these are the problematic resonances that occur here. So the reason that these measurement-induced state transitions might happen in these two regimes come from fundamentally different terms in the Hamiltonian. In other words, in the left-hand side, it would be absolutely terrible to make the rotating wave approximation, and on the right-hand side, you could do it, but obviously you can't truncate to the lowest two energy states of the transmon. Okay. So now let's talk about how we characterize measurement-induced state transitions in an experiment so that you can take these methods home with you and study them with us. So the first thing that we need to do is we need to track our so-called dress resonator frequencies. I'm just going to briefly explain the setup. So we have a quarter wave readout resonator, which is capacitively coupled to a frequency tunable transmon. This quarter wave readout resonator is also capacitively coupled to a Purcell filter, which allows for a fast readout. We measure this circuit in reflection using this circulator, and then the scattered signals move into our readout receiver, which consists of things like a circulator, quantum limited amplifier, a HEMT like we were just hearing about, and then ultimately some room temperature digitizer, which we use to infer the state of the system. To measure these dress resonator frequencies, what we do is simple. We either prepare the qubit in the ground or excited state, we vary the bias, and we perform resonator spectroscopy. And what this does is it furnishes a lookup table between our dress resonator frequencies and our qubit frequency and state. Now, why this is important is that all of this measurement-induced state transitions physics is really naturally explained in terms of photon numbers and qubit frequency or qubit resonator detunings. And so you really need some accurate way of keeping the photon numbers in your experiments controlled and approximately fixed as you consider multiple qubit frequencies. So this is just a fit to this dispersive model. Seems to work quite well. Now, the next thing that we need to do is we need to understand how fast our resonator empties. This is kind of a trivial statement, but if you remember, the way we measure these state transitions is we poison the resonator. We then want to let the resonator empty and figure out what state the qubit is in. So it would be very bad to have photons from this poisoning pulse carry over into our measurement or our final measurement of the conditional probabilities. So the way we do this is we drive the resonator on or near resonance. The system brings up because it stores energy. When you stop the drive, the resonator starts to decay exponentially, and we can fit this to just an exponentially decaying model to extract the resonator's energy decay rate. Why this is important is that this kappa, the resonator's energy decay rate, tells you how long you have to wait for the resonator's energy to decrease by a factor of 1 over E. And typically in our experiments, we wait something on the order of 7 inverse kappa to 10 inverse kappa to ensure that the system has fully returned to vacuum. Okay. Now, the last thing that we need is an extraction of the resonator photon occupation. The way we do this is using AC Stark spectroscopy. So we drive the resonator into the steady state. Once the resonator reaches the steady state, we apply a variable frequency qubit spectroscopy pulse, and we find where the average qubit frequency is shifted. This gives us a lookup table between resonator probe power and the number of photons in the resonator, assuming that we know chi. And fortunately for us, from this calibration, we know chi at any qubit frequency that we're operating at. Okay. The last thing is, of course, you need IQ clouds. So you need these reference centers in order to figure out where all of the qubit population is going to. So in this case, we can discriminate between the qubit 0, 1, and second excited state. But actually, we have pretty decent discrimination even to states 3 and 4 in this system. This is just an example. In subsequent plots, we kind of crudely define this notion of an outlier state, which is basically any IQ shot which lands 3 sigma outside of the centers corresponding to the qubit 0 and 1 states. And from our point of view, basically anything that isn't 0 or 1 is very, very harmful. So hence the definition. Okay, so putting this all together, we prepare the qubit in 0 or 1. We bias to a particular qubit frequency that we want to study measurement-induced state transitions at. We drive the resonator to the desired photon occupation for 1 microsecond in this case. We wait 10 inverse kappa for the resonator to empty, and we ask what state did the qubit end up in. This is just showing you one example of that for a given choice of qubit frequency and photon number. So the left is just the calibration clouds that I was showing you before. And then these right 2 images correspond to the preparation of the 0 and 1 qubit states. Now, we can do this in 2 dimensions. So we can kind of vary the resonator photon number and qubit resonator detuning almost continuously, and then we can look at what these images look like. Now, I know this figure is a lot to unpack, so let me try to explain what's going on here. The left column of images correspond to the preparation of ground. The right column of images correspond to the preparation of the first excited state. An ideal QND measurement would give you bright yellow on these 2 here, and then everything else should be dark blue under ideal circumstances. Now, of course, during measurement, if you prepare the excited state, you have things like T1 decay. So what we really want to do is focus on this lower panel here, where we're looking at basically the leakage that the measurement is inducing. We notice 2 or 3 interesting trends. The first one is that these structures seem to kind of band together. So you have these regions of bad streaks, followed by dark blue, followed by bad streaks, followed by dark blue. So this is kind of interesting. Another overwhelming trend is that as the qubit resonator detuning decreases, the photon numbers at which these leakage events occur seems to also decrease. This is bad because as the qubit resonator detuning shrinks, this is also where your measurement is getting more optimal. So it's kind of penalizing you for making a more optimal measurement system. And then finally, it seems that the ground state, for whatever reason, is a little bit more robust to these state transition errors. In other words, if you fix the number of photons you're using at 10, you have a lot more qubit frequency to operate at for the ground than you do for the first excited state, judging by just these colors here where I'm crossing all of these features. Okay, so I want to talk quickly about some experimental observations. So the first thing I want to say is that these features appear to be strongly time-dependent. So we can do this measurement-induced state transitions experiment along a fixed axis. So if I go back here, it would just be a line cut along here. It actually corresponds to this dashed line that I'm showing you. And then we can look at outlier probability as a function of average photon number. To do this along a single cut takes about 1 second for both qubit states using 5,000 averages per power. And then what we can do is we can wait 1 minute and then repeat the experiment. Wait 1 minute, repeat the experiment, wait 1 minute, and then repeat the experiment. What we notice is that these features in outlier probability appear to move, so these solid lines just correspond to the first realization of this experiment, and then these kind of translucent lines are showing you subsequent realizations. And why this is important is that you can imagine that you go into the lab, you choose some readout power and readout frequency you want to operate with, and here things look pretty good. 2 minutes later, a cosmic ray or gamma ray strikes your substrate. It liberates a bunch of offset charge, changes things, and then now, all of a sudden, you're leaking really quite badly. So that kind of goes into the next point is, why is this motion happening? And it turns out to be basically due to charge noise. So we ruled out a bunch of potential candidates, one being TLS, one being 1 over F flux noise, and indeed charge noise seemed to be the leading culprit. The first reason is that these state transitions are occurring due to resonances with very high excited states in the transmon, which are extremely charge sensitive. And then the second is that kind of the stability of the system really seemed indicative of charge noise processes rather than these other like 1 over F noise or shot noise and things like that. So charge noise in transmons exhibits some very quasi-static noise, and this is really what we're seeing in the experiment. Okay. So coming back to a little bit on the mathematical side, this is just an example of what one of these RWA strips looks like in this particular configuration when our resonator is below our qubit. But what we did here was we analyzed this system in the bare eigenenergy basis, but we kept the offset charge fixed. So the first thing that we wanted to do was include the offset charge. And what you see is that now what wasn't a problematic resonance before between the 0 and 9th excited state at a particular choice of offset charge can become problematic. So along the length of each of these states, we're just varying the offset charge and showing you what the resulting eigenenergies look like. So this is problematic, and then similar things can occur, of course, between the qubit's first excited state and maybe the 8th or 7th excited state of the transmon. So this is really a nasty problem. Now, the other interesting thing is that the problem gets even worse when you start to consider the dressed eigenenergies. So when you turn on photons in the resonator, because these coupling strengths grow as the square root of n, the charge noise inherited by these higher states is actually pretty significant even in the 0-1 subspace. And so this is telling you that Really, this charge noise is a nasty problem that gets pushed onto the qubit 0-1 manifold, even if it's deep in the transmon limit or has a high EJ over EC ratio. Now, maybe an avoided level crossing is worth 1,000 words. So basically here what I'm showing you is just an example of a resonance that occurs which couples the qubit 0 state to the 9th excited state. And remember that this offset charge is not controlled by us, but really something that just drifts randomly in our experiments. So this is a big problem. Okay. Now, the next question that you might ask yourself is, if you're connecting the qubit state to one of these 9th or 8th or 7th excited states, how difficult is it to reset the qubit following one of these events? So what we did was we modified our measurement-induced state transitions experiment by adding a variable delay gate followed by this reset protocol that I was explaining earlier, based off of adiabatic swaps. These panels are kind of similar to what I was showing you before, but let me explain the differences. So the left column still corresponds to the preparation of ground. The right column of images corresponds to the preparation of the excited state. The x-axis is qubit frequency, y-axis is average photon number, but now what's being varied across rows is this delay time between when this measurement-induced state transition occurs. You can really think about this as just like a qubit measurement in general, and when we apply this reset gate. What we notice is that, and then one more thing, the color scale here is reset error. So this is the probability of not finding the qubit in its ground state, given that you prepared it in either 0 or 1. So both of these axes, or these color axes for the left and right-hand column, are just reset error. What we notice is that at short times, a significant amount of leakage or reset error is occurring, and as we increase this delay time, we see that it's kind of cooling off. This is demonstrated by these hot features here. The color scale here was calibrated so that dark blue basically corresponds to a perfect reset, or what we did was we prepared the second excited state and first excited state. We applied this reset gate and we saw how much reset error we had, and that's how we capped things out. So this is really suggesting that we're dealing with leakage far beyond state 2. To put these numbers into perspective, because maybe a microsecond doesn't seem that long to some of you, a typical error correction cycle for a superconducting circuit may be on the order of 200 to 500 nanoseconds. And so you're producing these leakage events which could live for many, many error correction cycles. And this is extremely problematic for decoders. It's also just extremely problematic for 2D grids in general, because this leakage causes very big problems as it, bounces around and exchanges with other data qubits in the system. So measurement-induced state transitions produces very long-lived leakage, and this is, a really big problem for us. Now, these red lines that I'm showing you here were predicted theoretically from Mustafa, and we actually used them in our surface code experiment to basically say that you shouldn't operate with photon numbers that are above this line because you're going to hit leakage. So this was a theoretical prediction. You can look at that archive preprint that I linked, and you can see how it was computed. But nonetheless, you can see that a large fraction of the qubit's operating bandwidth in terms of both frequency and powers that are available to you are being completely suppressed by basically this process. Okay. Maybe just to talk about future directions, because I promised it in the title. There's a couple of interesting things that you might be able to do to kind of solve this problem. So the first thing is that rather than using a fixed frequency transmon, we might be able to take a page out of the Fluxonian playbook and shunt our qubits capacitor with a superinductor. What this would do is it would basically kill off this low-frequency charge noise process that was destabilizing our readout. In other words, if we chose a point that wasn't inducing leakage, then later on in time it shouldn't be inducing leakage either. And that is not true in the transmon because you don't have this inductive shunt. This was explored in 2019 for different reasons, because this inductive shunt also gives you an overall quadratic parabolic landscape which stabilizes the transmon. And what they found there was that this looked like a pretty promising adaptation of the readout circuit to basically stabilize it from the point of view of measurement-induced state transition. So this is a pretty interesting proposal, and I look forward to seeing people in the community try this and determining how well it works. Another interesting proposal that dates all the way back to 2015, and I know probably people in the audience are wondering, well, why has no one tried it, is this longitudinal readout scheme. The idea here is that you actually could really significantly modify the way that the transmon and resonator are coupled to, and instead of this XX interaction, which you typically operate in this dispersive regime where these two systems are far detuned, you can realize an XZ interaction. And at least in theory, this should no longer allow for swapping. This XX term, which is causing all of these problematic state transitions, should no longer be able to occur. There's other advantages of longitudinal readout, such that one interesting thing is that the pointer states corresponding to the ground and excited state actually displace optimally as a function of time. So instead of an ideal phase separation of pi over 2, they actually have a phase separation of pi. SNR per photon as well. Okay, with that I'd like to conclude. So these measurement-induced state transitions produce long-lived leakage states that are detrimental to surface codes. This holds independent whether the resonator is above or below the qubit. If you generate the 6 excited state, you generate the 6 excited state. Another interesting thing which I was trying to point out in my talk was that these measurement-induced state transitions occur for fundamentally different reasons depending on the relative hierarchy of frequencies in the problem, and I hope you found that interesting. This measurement-induced state transitions problem is further exacerbated by offset charge jumps in the transmons, and as you know in the superconducting qubit community, that's really our workhorse. And then finally, to work around this problem and really achieve these ultra-fast measurement speeds that are desirable for the surface code, it may be optimal to really fundamentally adapt how measured qubits look. And you may even want to add an additional qubit, which is just responsible for measurement, to avoid this leakage problem altogether. So with that, I'd like to thank you for your attention and take questions if there are any.